So our today topic is eigenvalues and eigenvectors. So our today's content of the topics content or lecture content of the are eigenvalues and eigenvectors. General approach to find eigenvalues and eigenvectors. Here we define first of all what are eigenvalues and eigenvectors. Then we use some common approach or some common methods to find these eigenvalues and eigenvectors. So first of all, we see its definition of eigenvalues and eigenvectors. An eigenvalue of a square matrix A matrix is a square matrix. Square matrix mean its number of rows and number of columns are equal. Here n cross n shows the number of rows and number of columns, and Ij means here I is row and J means column. So here we have a matrix and square matrix, and in the previous lecture we will learn learn that what is square matrix, a matrix whose rows and columns are equal. Then in a square matrix, first of all we have a matrix or which is a square matrix. Then an eigenvalue is a number, and we denote this number or eigenvalue by lambda. It is just an notation of eigenvalue. Don't be confused with it. Such that the vector equation is ax is equal to lambda x, where x is not equal to 0. X is not equal to 0 mean here A is our capital A is our matrix whose eigenvalues we have to find. X is our solution vector or x, and here x is not equal to 0. Because when we put here x is equal to 0, then 0 multiplied by lambda, and our goal is to find eigenvalue lambda. But here is eigenvalue multiple is 0, so it is also 0. So we have nothing to find. So that's why here x is equal to 0. Has a non-zero solution vector x. The solution vector x is then called an eigenvector. From here, we find some solution vectors. These are called eigenvectors of the matrix A corresponding to the eigenvalue lambda. For each eigenvector, we have each for each eigenvalue, we have each eigenvector. So how many eigenvectors we have? It depends upon our eigenvalues lambda. So for example, here 3 0 1 2, this is the matrix, square matrix, because it has 2 rows, this and this one, and it has 2 columns, 3 1 and 0 2. So it is a square matrix, and we multiply it with x. Here x is 1 1. It is totally upon to us what is x. So this, when we multiply this, we have 3. Okay. So what is the common in this? 3. Take 2 common, this we have 1 1. You see here x is 1 1. So this 3 is additional. So this 3 is our corresponding eigen value. So if we if we write the same matrix and put 0 1 instead of 1 1, then we multiply and we got the result. So 2 common 3 from these, and we have 0 1. Here we have eigenvalue 2. So when we multiply, here I take 3 different examples and want to show how we calculate eigenvalue, in which case we have no eigenvalue. So here I multiply 1 1. 1 1 is our educated guess of the matrix or x. So it is totally upon to us. Here I take 1 1 as a x. Here I take 0 1 as a x, and here I take 1 0 as x. Now I multiply these x with our matrix, given matrix whose eigenvalues we have to find. So after multiplication, we have a resulting matrix. Then you see what is common in this resulting matrix. Take common if you can. So here we clearly see that we take common 3, because 3 is multiple of all these entries are multiple of 3. So when we took common 3, here we have 1 as a, because 3 is common here. So this is the same x as we put it here. So if compare this value in our this equation, ax is equal to lambda x, this is our a, this is our x, is equal to, after multiplication we got x and lambda. So with the, when the element which is written here with the x matrix, then this is the eigenvalue. Here our eigenvalue is 3. Similarly, conclude here. Here our eigenvalue is 2. So now I multiply, I choose one that matrix x as a x, and here I choose 1 0. Multiply it, and you see here you have no common multiple. If you have no common multiple, then you have no eigenvalue. So it is totally depend upon us how we calculate this, and this is totally depend upon our choice of x. So for this x we have no eigenvalue. Here you analyze one thing, our matrix remains same, but by changing x our eigenvalue change and vary, and in some cases it has no multiple and no eigenvalues. So an eigenvector is a vector different from the null vector. It is different from null vector which does not change the direction in the transformation. Transform means shifting one frame of reference to another, except if the transformation turns the vector to the opposite direction. The eigenvalue is the value of the vector's change in length. So eigenvalue is the value of change. Here I explain about physical interpretation of eigenvalues. So here physically eigenvalue, what eigenvalue do? Eigenvalue change the length of the direction or stretch it. You mean you understand what is stretching? Stretching is the changing the length of the matrix, and in transformation. The word eigen is German word, and it has the meaning. What is so this is the German word, okay. So but we learn from here, I learned from here what is the equation of characteristic equation of the our matrix, and for finding eigenvalues, and we study about an analysis about x, and have about eigenvalues can be vary from matrix to x to x, or depends upon our choice of x. So next, some physical interpretation, explain some more physical interpretation. Here, what is the physical interpretation? The image of is changed in such a way that the red arrow does not change its direction, but the blue one changes. Here, you see these arrows, okay? The red arrow and the blue arrow. Therefore, the red vector is an eigenvector of this transformation. Blue one is not. When you rotate this picture as this, and you see these are the vectors, but here and here the direction of these eigenvectors are changed. So the vector whose direction is changed, then it is eigenvector, otherwise it is not eigenvector. So from changing the direction, you conclude clearly about the eigenvector. So by changing the direction of the vector, the resulting vector is our eigenvector of the transformation. Okay, so blue does not change its direction, so it is not a eigenvector, but red is changes its direction, so it is eigenvector. So next we see, since the red vector does not change its length, its eigenvalue is 1. Red vector does not change its length. You see here, its length remains constant, just its direction changes. So by the changing of directions, we estimate it is eigenvector. But now here we have to find its length. In many cases, the eigenvector can change its length, but here the length remains constant, but only direction changes. That's why here we say the eigenvalue is 1, because eigenvalue is 1, that's why its length remains constant. If eigenvalue is 2, then its length is double, and if eigenvalue is 3, then its length is triple 3 times, and if it is -3, then its length will decrease -3 times. So from its constant length, we estimate that its eigenvalue is 1, because multiply anything by 1 does not make an effect of our answer. So the value lambda is an eigenvalue of n cross n matrix A if and only if determinant of A minus lambda I is equal to 0. The roots of the above equation, determinant of A minus lambda I, are the eigenvalues of A. Okay, so this is determinant. Okay, so next I will explain the method how to find determinant. Here you just understand this is the determinant and A minus lambda I, and this is the whole equation is known as characteristic equation. Okay, so the roots of the above equation, definitely it is the equation, then it has some roots and are the eigenvalue of A. So roots of this equation are the eigenvalues and the nth degree polynomial. When you take its determinant of A minus lambda I and then take its determinant, then you have some polynomial, and the nth degree polynomial is called the characteristic polynomial of A. Then it is called characteristic, and this is the characteristic equation. Okay, from characteristic equation we have to determine characteristics polynomial. The eigenvalue of A can be real, complex, and repeated or multiple. So eigenvalue of A may be a real number, may be a complex number, or maybe multiple repeated more than one real numbers. So here we make a clear idea about eigenvalue. Eigenvalues not necessary in all the cases it remains real number. In many cases it is complex number, and in many cases it is multiple of many complex numbers. There could be most and distinct eigenvalues of A. Okay, so there could be at most n distinct. What is n here? N is over the degree of polynomial. Okay, so we have an equation of degree 3, then we have at most 3 eigenvalues, different from each other. So we have at most 3 eigenvalues. Okay, if we have 3 degree polynomial or characteristic polynomial of A, so n at most, and here at most word is very important, because at most mean it can be less than n or equal to n, but not greater than n. For example, you have a 4 degree polynomial, characteristic polynomial equation, then you have at most 4 eigenvalues, possibilities of 4 distinct eigenvalues, or less than 4, but 5, 6 is not exist here. Okay, once eigenvalue lambda is known, first of all we have to find eigenvalue. When it's known, an eigenvector corresponding to lambda can be determined by solving the homogeneous system, and this is our homogeneous system. Homogeneous system is the system where Ax is equal to 0. This is the null vector, and whose a vector whose one hand side or right hand side is equal to 0 or null vector, then it is homogeneous system. So we write this homogeneous system and solve this homogeneous system, and we determine the eigenvalues lambda from this homogeneous system. Okay, so all these steps are included in the procedure to find the eigenvalues and eigenvectors. These are our main procedures to find eigenvalues and eigenvectors. So now we proceed next. Procedure to find the eigenvalues and eigenvectors. Now I explain the previous concepts here with the help of example and want to show how we calculate the eigenvalue. So in the previous slide we discussed about major steps. Now we implement these steps on one example and show how we find the eigenvalues and eigenvectors. So here we have a matrix A, and by seeing its representation, you have a clear idea that it is a square matrix and it has 3 rows. 1, 2, 3. It has 3 rows and 3 columns. So number of rows and number of columns are equal to 3. So we have it a square matrix. Then the second step is to write a characteristic polynomial of P of lambda. Characteristic polynomial can be represented, or its characteristic polynomial notation is P of lambda. P of lambda is equal to determinant of A minus lambda I, and you know determinant means this bar represent determinant. A minus lambda I of I here. What is I here? I is identity matrix, and you know identity matrix of 3 cross 3 set is 1. Identity matrix is here 0 0 sorry 1 0 0 0 1 0 0 0 1. This is our identity matrix of 3 cross 3 matrix. Okay, so multiply lambda from this. Then we multiply lambda from this. Then we here we have lambda, here we have lambda, and here we have lambda. So if I write it in a clear form, then I write it here as this lambda. Here 0, here 0, here 0, here lambda, and here 0, here 0, 0, and this is lambda. So this is our AI. This is our AI. Now we minus A. We have to minus A in AI. So 4 minus lambda is this. 1 minus 0, it is 0. Okay, not 6. 4 minus 1 minus 0, 1 remains same. 0 minus 0, it is 0. 2 minus 0, 5 minus lambda, and 0. So all these we calculate from this method. Okay, so after calculating A minus lambda I, next step is to determine the complement of our this determinant of this. So what is the determinant? How we find the determinant? So determinant is write first value here, and then you have to multiply this, then minus this. Okay, when you calculate this step, then you have to write this element from here and write minus 1 minus as a bracket, and multiply these and these. Okay, then in the next step you write multiply this is 0 and multiply these 2 terms. Okay, or in other words you say whose first of all we eliminate this row and this column. Okay, in second step we eliminate this row and this column. Okay, and in third step we eliminate this row and this in this first column, first row and last column. So from this we calculate the determinant, and now we multiply 4 minus lambda to 5 minus lambda into 1 minus lambda and multiply it, and we have the resulting this. It is the simple basic algebraic multiplication. Here no is rocket science used. So that's why 1 minus lambda and lambda square minus 9 lambda plus 18. So the roots of the polynomial equation, characteristic polynomial equation. What is P of lambda? Polynomial characteristic equation of the eigenvalues of the matrix A are as follows. So when we calculate it and put it is equal to 0, then 1 minus lambda is equal to 0, lambda minus 6 is equal to 0, lambda minus 3 is equal to 0. So from here I have lambda 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is equal to 6. So here I determine all these values. Okay, so next we see how these are our eigenvalues. Now we have to find eigenvectors with the help of eigenvalues. So let's see. Eigenvectors say v1. For example, we have 3 eigenvalues. So we have three eigenvectors. So let's suppose our first eigenvector is v1. v1 can be determined by solving the following system. A minus lambda 1 I into v1 is equal to 0. 4 minus lambda 1, 1, 0. 2, 5 minus lambda 1, 0. 7, 2, 1 minus lambda 1. These are here, this is our characteristic polynomial. Here I write v1. v1 has three entries, and I suppose v1 is equal, v is equal to v1, v2, v3, and so on. So this is the zero polynomial, and this is our 0, 0, 0, and we write multiply it with this, and we multiply this with and it is equal to 0. So let us solve the linear system by the Gaussian elimination method. And for this, the augmented matrix is formed as augmented matrix is formed as write these and write the dot lines, and you have to write right hand side. Here we have 0, 0, 0. So you have to find. Now you have to solve this system, or in other words, you have to solve this by Gauss elimination method. In Gauss elimination method, you have to find reduced row echelon form. So you have in reduced row echelon form, your first step in your mind is make this 3 as 1. Then all the entries below this pivot element is 0. Then remove second element of row is 1. Then all other elements above and below this pivot element make 0. So finding eigenvalue, here what are we doing? We calculate eigenvector and corresponding to lambda 1 is equal to 1. Here first of all, we suppose our one eigenvector lambda eigenvalue lambda 1 is equal to v1, and corresponding to that eigenvalue we calculate an eigenvector, it's v1. Okay, so next we see what is the eigenvector. Calculate this by Gauss elimination method, and if you have not studied about Gauss elimination method, then you first of all you have to learn about it, how we calculate. And here I just give a simple and clear idea about this. In all, at the end you will go such type of matrices. First one, and all this one is pivot element, and all the entries below this pivot element or above this below this pivot element 0. Here you see our third row is equal to 0, 0. So our third vector mean v3 is free variable. Free variable means we can choose it arbitrarily according to our choice. So we have the right to choose it 1, 2, or 3, or anything else, because it is a free variable. It does not depend upon any other thing. So here v2 is equal to 0, because this vector is v1, v2, and v3. This column is for v1, this column is for v2, and this last column is for v3. So here you see, here v3 is equal to 0, because here in third row all the elements are 0. Here in second v2 column is 1, so v2 is equal to 0, because our right hand side is equal to 0. Here we have v1 and v3. v1 minus v2 is equal to 0, and we know the values of v2. v2 is equal to 0, so that's why v1 is equal to 0. And from here we have we find v2 is equal to 0, v1 is equal to 0, but here we left v3. So as we say v3 is arbitrary, so choose let's v3 is equal to 1. So v1, v1 is equal to v1, v2, v3. Here t is transpose. You can write it here as a column matrix without transpose, and it is your just a notation, so don't be confused with it. So v1 is equal to 0, 0, 1. So here v1 is equal to 0, that's why I write it here 1. v2 is equal to 0, that's why I write it here 0. v3 is equal to 1, that's why I write it here. These are the required eigenvectors. Okay, so this is our resulting eigenvector. Now we learn we have to find the second eigenvector with respect to our second eigenvalue. In our previous slide we have lambda 1 and we find v1. Now we have lambda 2, our second eigenvalue, and we have to find eigenvector corresponding to that eigenvalue. So all the repeat all the procedure as seen our previous slide. Solve the system by Gauss elimination method and determine either one of them is a free variable or not. And this is the just augmented matrix, and you know how we write augmented matrix, then apply the procedure of Gauss elimination. And here you note our second row, all the elements of the second row is zero. So here v2 is arbitrary elements. We can choose or free element, free variable. So it when it is a free variable, then this here this is v2. So 5 v2 plus 2 v1 is equal to 0. Let's choose v2 is according to our choice. So let's do v2 is equal to minus 2. It is totally upon to us. Here I let v2 is equal to minus 2. It is totally your choice. You let v2 is equal to 5, v2 is equal to 10, because it is arbitrary. So v1 and v3 according to putting the value of v2 in these two equations, and you have to find by simple just solving the equations, simple equations as we basically solve these equations, or v1 and v2. And here we have v2 is equal to minus 2, v1 is equal to 2, and v3 is equal to 5. So we have v2 is equal to 2 minus 2 and 5, and here is the transpose. You can also write v2 as in the form of these 2 minus 2 and 5 without transpose. If you write it in here a vertical form, then you have to remove this transpose, or if you put this transform, then you have to write this as horizontal form. Okay, so this is the just basic notation of this. So this is where v2. Now we calculate similarly v3 corresponding to our eigenvalue lambda 3, and it is equal to 6. All these steps and all the steps of previous slides are repeated here. And first of all, find augmented matrix, then solve this augmented matrix by Gauss elimination method. And after solving this by Gauss elimination method, you have to find the eigenvector, or its name is v3. So note one thing here, our again our last row is 0, so our v3 is our free variable, so we choose its value according to our time. According to this, so using this form, we with equation 3 gives the following procedure. Here v3 is equal to this, and solve this, and v2 and v3, these equations are this. Let v3 can be chosen arbitrarily, so let v3 is equal to 11. So v3 is equal to 11. If we put 11 here, then this 11 multiplied by this 11, cut these two values, and we have v2 is equal to 10. Okay, so v3 is equal to v3 is equal to 11, or v1 is equal to 65. So v3 is equal to 65, 10, 65, 10 and 11, our third eigenvector. So you see here we have 3 eigenvalues, and corresponding to these 3 eigenvalues, we have 3 eigenvectors named v1, v2 and v3. So next we see about eigenvalues, more points, some properties of eigenvalues. Why we use these properties? What are the main features that we spent our hour to learn about them? Because our time is precious, and when we spend our time on some topic, so we have a clear idea what are these what are the properties of that topic, and how we use, and how with the help of this topic how we can solve our problems of mathematics and other linear algebra easily. So that's why properties are very important. And here we discuss some properties of eigenvalues, and suppose that lambda 1, lambda 2, lambda n are the eigenvalues, and so on are the eigenvalues of n cross n matrix, and here A is equal to Aij. Following are some important results about the eigenvalues. Trace of A. Trace of A means sum of all the diagonal entries. Trace of A, you know, sum of all the diagonal entries. Diagonal entries mean all the entries are whose mean A11, A22, A33, or A11 mean I mean I here I mean number of rows, and I mean number of columns, mean all the elements whose order with respect to row and column are equal. So determinant of A, if you have a very large matrix and you have to find determinant of A, then it is very difficult task to find about determinant, because it make more calculations and time taking task. So that's why if you know about eigenvalues, then you have to multiply all these eigenvalues, then our resulting matrix is our eigen determinant of A. So multiplication of all eigenvalues give us determinant of A without large and calculations. So spectral radius of A mean rho of A, and it is the maximum of all the absolute values of eigenvalues of A. So rho of A always less than is equal to matrix of norm of A, or matrix norm, or this is the our matrix norm. So lambda 1, lambda 2, so on lambda k are the distinct eigenvalues of a matrix A corresponding to the eigenvectors x1, x2, and so on xk respectively. Then the said eigenvectors are linearly independent. Are distinct eigenvalues corresponding to eigenvectors, then the eigenvector, if we have distinct eigenvalues and distinct eigenvectors corresponding to that eigenvalue, then our eigenvectors are linearly independent. And here what is linearly independent is discussed we in our next terms. So here we see what is eigenvalue and eigenvector, how we find eigenvalues and eigenvectors, and then we determine number of eigenvalues and number of eigenvectors at most, and then we see some properties of eigenvalues and eigenvectors.